Okay, so then the next step is determine the temperature solution for every eigenvalue. So if you think about it, our temperature solution is the product of Tx and Ty. We've now got a solution for Tx, it's given here. We've got a solution for Ty, it's given here. We have one of these for every one of these eigenvalues, right? So if I multiply this guy and this guy, I had to get a solution for temperature, and that's what I've done here. So Ti is equal to Txi times Tyi. So Ti is equal to C1i times the sine of lambda ix times, in brackets here, C3i times cosh of lambda Iy plus C4i times sinh of lambda Iy. So this is a solution for temperature, right? I have not just one of these, I have an infinite number of these, one for every single eigenvalue. A couple things to sort of mention here. I guess one thing is these constants that I have here, C1, C3, and C4, these are undetermined constants, right? We still have to figure out what they are, which we'll do probably next time. But if I take C1i and bring it inside of these brackets, I'm going to have C1i times C3i, and over here I'm going to have C1i times C4i. And I hope it's pretty obvious that if I have the product of any two undetermined constants, then that's just another undetermined constant. There's no need to keep those two undetermined constants. So I don't really need to keep C1i anymore, right? I can absorb that into C3i and C4i because, it's all just undetermined constants to me at this point. So here's my solution for temperature. And again, I get one of those solutions for every eigenvalue. And this is a really good place to stop and check and make sure that you haven't screwed up, because this solution doesn't solve our whole problem yet, right? If you think about it, this is our whole problem, right? Our whole problem is this partial differential equation, these two boundary conditions in x and these two boundary conditions in y. And here's our solution to this point. This solution won't do all of these things. If it did, we'd be done. That'd be great. But it should do some of these things. So which parts of this problem should this solve? Well, we got this solution by breaking this partial differential equation up into Tx and Ty, right? And we solved each of those separately, and then we multiplied them back together. So hopefully this solution will solve this partial differential equation. And then the other thing we did is we solved our eigenproblem in such a way that it better satisfy this boundary condition and this boundary condition. So with any luck, assuming I haven't made a mistake, my solution here should satisfy this partial differential equation, this boundary condition, and this boundary condition. I have not done anything yet that would help me solve this boundary condition or this boundary condition. So we have not yet enforced the boundary condition at y equals 0 or the boundary condition at y equals h, right? The boundary conditions in the non-homogeneous direction we still have to deal with, but we've done the rest of it, and we should check and make sure that actually works, right? So you can do this a couple ways. This is again a place that I think Maple's pretty handy. I can just plug this function into Maple and specify what these eigenvalues are, and then just verify that, yeah, it does this, and it does this. So let's look at how you would actually do that. So let's see if I can make this work. So somewhere I have Maple open right here. I put this code up on the website so you can look at it if you want. I start with restart, which just clears the memory. Then I'm going to put in my eigenvalues, right? So my eigenvalues are given by this equation here, but you need to recognize that I here is not just anything, it's an integer, right? So I have to specify to Maple that I is an integer, and I do that with the assume command right here, right? I'm going to assume that I is an integer, and you can do all kinds of things with the assume command. You put the first argument is the variable you want to assume something about, and the second argument is what do you want to assume about it. In this case, it's an integer. It could be positive, negative, real, whatever. You can use the assume command to specify that. And then what you'll see is any place else that I appears, it's got this little squiggle after it. And that little squiggle means there's some assumption about I. It's not just a variable that can be anything. It's a variable that has some specifications on it, right? So then I put in my eigenvalues. So lambda is 2 times I minus 1 times pi over 2w. And here is another thing that's worth mentioning. Pi you can type in as little pi or big pi, right? Little pi, we said, was the numerical value of pi out to some number of significant figures. Big pi, so capital Pi, is actually the symbolic pi, right? So it will be interpreted as pi, and that's the one you want to use here. You want to use pi. Okay, so I put in my eigenvalues, put in this part here. Now I got to put in this function, right? So this is a function of x and y. So this is how you put in a function of x and y, right? You say t is assigned to, and then this parentheses x comma y with the little caret after it means it's a function of x and y, and here's the function, right? So sine lambda x times c3 cosh lambda y plus c4 sinh lambda y. So this is my function. Okay, so what did we say this function needs to do if I haven't screwed up yet? The first thing it needs to do is evaluate to 0 at x equals 0. So I can use this function and just plug in 0 for the first argument, and I better get 0, which I do, so that's good. The second thing it needs to do is evaluate, if I take the derivative and evaluate it at x equals w, I also better get 0. So here I have taken the differential of my function with respect to x and evaluated it at x equal w, and again I get 0. So that's good. Those two boundary conditions in the homogeneous direction appear to be working. And the last thing I better make sure this does is, if I take two derivatives of this function with respect to x and add it to two derivatives of the function with respect to y, I better get 0. So that's what I did here, right? I took two derivatives of my function with respect to x, I added it to two derivatives of my function with respect to y. I got this big mess, but if I simplify that big mess, I get 0, right? So at this point, everything seems to be working pretty well, right? I have solved, I mean, if you count each of these equally, I've solved, what, 60% of my problem, and I'm left with 40% down here, right? So it turns out this last 40% is tricky, right? But, you know, again, not any trickier than what you've done so far, and kind of interesting. So that's what we'll do next time, is we will continue down the path with where we're at right here, and we'll force this function to satisfy these last two boundary conditions, right? So we're in kind of good shape because we have two undetermined constants left to choose. In fact, if you think about it, we have many more than two. We have two of these for every single eigenvalue, so we have 2 times infinity of these undetermined constants left to choose. So the rest of the problem is really choosing those undetermined constants so that the right thing happens at these non-homogeneous boundaries.